Advent of code, day 16. Here we go. Day 16, packet decoder. Hexadecimal, your puzzle input, 4 bits of binary data. Okay. The bits transmission contains a single packet at its outermost layer, which may contain other packets. Each packet begins with a standard header. First 3 bits encode the packet version, and the next 3 bits encode the packet type ID. Okay, one line. Bits equals stir.cars.mapDo. Oh, wait. .2i16. Value to i16. To be bits equals .2s2.cars.map to I flatten. Ba 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 ba. Okay. First 3 bits encode the version, next 3 bits encode the packet type. Type ID 4. The version is packet 6. Represent a literal value. Literal value packets encode a single binary number. To do this, the binary number is padded with leading zeros until its length is a multiple of 4 bits. Then it is broken up into groups of 4 bits. Each group is prefixed by a 1 bit, except the last group, which is prefixed by a 0 bit. These groups of 5 bits immediately follow the packet header. Okay, so that's 1, and then it starts with a 1, and then it starts with this 0, so that's the last group. Every other type of packet is a operator. Okay. Packets. Whoop do. Version equals 1, 2, 3, 4 dot shift 3. Shift 3. Version equals bits dot shift 3. Dot join dot 2i2. Type ID. operator that performs some calculation on one or more subpackets contained within. An operator packet contains one or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one of two modes indicated by a bit immediately after the packet header. This is called the length type ID. So if type ID equals 4, else digits equals continue first bit equals bits dot shift while first bit digit equals bits dot shift dot digits dot concat bits dot shift 4 while first bit equals 1 digits first bit equals bits dot shift value equals digits dot join dot to I2. All right, so it's an operator. Length ID equals bits dot shift if bits okay, I think I should reverse my bits array, but whatever. If length ID equals 0, else total length equals bits dot shift 15 to join dot to I2. Num packets equals bits dot shift 11 dot join to I2. The total length in bits of the subpackets contained by this packet. Then the next 11 bits number of subpackets. So this is packet version 1, ID 6. This is a 0, so it's 15 bits. That's the length of the subpackets. And then this is 4. Okay, 6 plus 5, and then what is B? Okay. Two, 4, 5. Okay, that makes sense. And add up all of the version numbers. Okay. version numbers equals 0. Version numbers plus equal version. While bits.any puts version numbers. Fit 774. Okay, that's wrong. Of hexadecimal encoded. Oh. Five. Puts version type ID. Puts literal puts operator length, total length, num packets, operator version 4, operator packet version 1. Oh. Wait. An operator. Wait, I got the 0 and the 4. An operator packet 4, which contains an operator packet version 1. This isn't right. ex2 ex2. Okay, so this has operator. Wait, if it's 4, version type ID. Puts bits. What's up, Eric? This is it's going okay so far. All right, let's make sure my my bit conversion thing is working. 110110. No, it's not. 1101. Bits equals B. Why doesn't this work? Puts oh no. Okay, I need to pad it to 4. B dot unshift 0 while B dot length zero zero 1 0. Lots of ones. Okay, now it's working. Uh, 934. Let's go. 37. Woohoo! All right, now that you have the structure of your transmission decoder, you can calculate the value of the expression it represents. All right. Sorry, I'm streaming. I didn't expect to get out of the leaderboard. Sum equals 0. Product. Product. Equals 1. Min equals 2. Max equals 3. 5. 6. Equals 7. Okay. Parent packet. Equals that sub packets packets, all packets, packet stack. Packet stack equals sub packets remaining packets remaining bits. Okay. So packet equals all right, so if it's a literal bits bits used equals len before len equals bits dot length bits used equals before dot length before len minus bits dot length nil num packets equals nil value equals nil. Okay, so if value I should read this more carefully. Now that you have the structure of your transmission decoder, you can calculate the value of the expression it represents. Literals represent a single number. The remaining type IDs are more interesting. Packet IDs with type 0 are sum of the subpackets, product of their subpackets, min, max, greater than, first subpacket is greater than the second, less than, one, less than, equal if they're the same. Okay. All right, so if it's a value packet, then we have packet stack dot last subpackets literal value. Literal value otherwise new packet equals subpackets, and then what do I call it? Remaining packets, remaining bits. Remaining packets is num packets and total length. Num packets, remaining bits, num bits. Okay, so then we need to add the new packet, packet stack, oh, wait. Shh. New packet equals that. New packet. Packet stack if packet stack dot last remaining packets, then packet stack remaining packets minus equal to 1, packet stack dot pop if packet stack last remaining packets equals 0, else packet stack dot last remaining bits minus equal bits used bits. If no value, packet stack new packet. JSON require JSON puts packet stack to JSON pretty generate if literal value, yeah, whatever. Num bit, oh, bits used. Num bits. Oh, total length. Last. Oh. Wait, why didn't that work? Okay. Do 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 do. Six. Subpackets 1, 2. Oh no, I need to store the version and type ID. New packet version equals version type ID. Literal 1, 2, version 6, version 2, version 0 sum. Okay. Def eval packet. Okay. For case packet type ID. Okay. When literal. When literal packet literal. When sum return packet literal if packet type ID equals literal. Subpackets equals packet subpackets dot map p eval packet subpacket. Subpackets dot sum when product when min max greater than less than equal subpackets dot min max greater than subpackets okay, so if it's greater than, if the value of the first subpacket is greater than the value of the second, it's 1, otherwise 0. Oh. Okay. Do puts eval packet packet stack. Oh, product. Prod equals 1 sub packets dot each val prod times equal val prod. Oh, sub packets. All right, 3. Let's go. Dang it. All right, not the right answer. Why do I end up with a sub packet at the end? That's kind of weird. All right, December 16th at ex2. ex7. '54. ex8. ex9. Okay. ex10. 1. Zero. Zero. Ex 1. Okay. It's working on all the examples. New packet. Am I doing this correctly? And that's not correct. Puts packet stack dot length 23. Okay, that seems wrong. puts summing prodding multiplying min of max subpacket 0. Let's do this. Subpacket 1. Depth. Print depth puts literal what? 113. There we go. Oh. Subpacket. Literal 1, literal 3, summing 1, 3, literal 2, literal 2. Else puts unknown. One. Five. 6. All right, so that's the sum of 1 and 2. 7 is 6 times 9. 8 is min 7, 8, 9, 9. Literal 5 is less than 15. 5 is greater than 15. Okay, so this looks a little off right here. So we have a 1 and a 3, which are summed. And then a 2 and a 2, which are product, and then this. Where does this come from? If okay, so let's see here. So we have our stack, and we think there are lots of packets. Anytime we see an operator, packet ID other than 4, number of subpackets immediately contained. Num packets is that. Total length in bits is this. Put packet stack remaining packets. Put using bits used now. Puts. $80 remaining, 62 used 1. Print packet stack dot length. All right, so we have our stack. Subpackets immediately contained. So when we get an operator pack, all right, so the idea is the top thing, the last thing on the packet stack should be a parent. And so we put things on yeah. So packet stack 0 should be the root. The last thing on the packet stack represents the parent. So when we see a packet, okay. Packet ID equals 0. Packet ID equal packet ID. Packet ID puts packet ID is a literal. An operator has num subpackets Oh, I'm not subtracting the bits from everything. Dang. Okay, that's tricky. Packet stack dot each parent packet stack dot each parent ancestor remaining bits minus equal bits used if ancestor remaining bits else is this the same thing I had before? I think so. Okay. Put packet ancestor removing bits used from and then this is while now Puts popping packet with no more bits. Yes! I did it! Yay! Okay, that one was hard. But I got on the leaderboard! 37th, that's what matters! Not so hot on part 2, though. What's up, Crush On? Alright, let's go back over this. Whew, this one was a doozy. Okay. Day 16, Packet Decoder. As you leave the cave and reach open waters, you receive a transmission from the elves back on the ship. The transmission was sent using the Buoyancy Interchange Transmission System, BITS, a method of packing numeric expressions into a binary sequence. Your submarine's computer has saved the transmission in hexadecimal, your puzzle input. The first step of decoding the message is to convert the hexadecimal representation into binary. Each character of hexadecimal corresponds to 4 bits of binary data. So, we have our string input. We loop over its characters. For each character, we convert it to a number using Ruby's, like you can pass in the radix here. And then we convert it to a string, but in binary. So we convert it to an integer as hexadecimal, then to a string, back to a string via binary, and then we get its characters. But if we do like 0 to string, that just returns 0, not actually 4 bits. So then we need to shove zeros onto the beginning, while if we have less than 4, and then those are the bits for that. And then we flatten all those bits. So puts bits.inspect. We get something like that. Those are our bits. So now we're doing stuff with packets. The bits transmission contains a single packet at its outermost layer, which itself contains many other packets. The hexadecimal representation of this packet might encode a few extra 0 bits at the end. Oh, these are not part of the transmission and should be ignored. Okay, I didn't get that memo. Every packet begins with a standard header. The first 3 bits encode the packet version, and the next 3 bits encode the packet type ID. So we're going through our bits. The version is the first 3 bits, and then we join them and convert them to an integer. The type ID is the next 3 bits, and we join those. That gives us 3 1s and 0s. We join them and then convert them to an integer in binary. First 3 bits encode the packet version, next 3 bits encode the packet type ID. These 2 values are numbers. All numbers encoded in any packet are represented as binary with the most significant bit first. A version binary sequence is 1100 represents the number 4. Packets with type ID 4 represent a literal value. So that's this case up here. Literal value packets encode a single binary number. To do this, the binary number is padded with leading zeros until its length is a multiple of 4 bits, and then it is broken into groups of 4 bits. Each group is prefixed by 1 bit except the last group, which is prefixed by 0 bit. So these are the bits of the literal value. So we get the first bit, which is this either one or the like signal of the group, and then we get the next four. We shove the next 4 bits onto digits. Then while that first bit was a 1, that means there's another group, and so we get the first bit of that group, and then add the next 4 digits into digits. Once the first bit is a 0, it'll break. And then we can get the literal from the digits by joining it, all the characters together, and converting it to a number from binary. So that gives us a literal. So in here, this is an example. Every other type of packet with ID other than 4, represents an operator that performs some calculation on one or more subpackets contained within. Right now, operations aren't important. Focus on parsing the hierarchy of subpackets. An operator packet contains one or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one of 2 modes indicated by the bit immediately after the packet header. This is called the length type ID. So this is the length ID. If we're not type 4, so we're an operator, so we get the length ID. If the length ID is 0, then the next 15 bits are a number that represents the total length in bits of the subpackets contained by this packet. So that's what that is. Total length is, we get 15 bits from it, and that's a number. If the length type ID is 1, then the next 11 bits are a number that represents the number of subpackets immediately contained in this packet. Cool. That's like mostly what you need to know for part 1. Basically, like in this one, this is a length thing. So given in 15 bits, and it's 27. And so the next 2 packets are 11 bits and then 16 bits. And so those use up the 27 bits. And so those are the sub things. Part 1, we parse the hierarchy and add up all of the version numbers. Turns out we don't actually have to add up all the version numbers. We can just use the bits. Yeah. We can use, or we can just, yeah, we don't have to build up the hierarchy. We get the versions. And so we can just add up all those versions. So that's version numbers set to 0, and then we add the version. And then I know, where's my part 1? Puts part 1 version numbers. Puts part 2. I'm getting rid of some of my other putsing. Cool. So that's part 1. So now for part 2, it turns out we do need to create that hierarchical representation. So let's go over how we do that. So we're going to have a stack of packets, because basically, like, when you use up a packet, it gets added to a parent. And so we need to have like the ancestor stack. So we'll start with something on the packet stack. Each packet will have some subpackets. It'll also keep track of how many remaining packets it has and how many remaining bits. We don't really know what the top packet does, so we just say it has tons of remaining packets and tons of remaining bits. And then I give it this ID, which doesn't, that was for like debugging, and I never really got to that. So after we've parsed a packet. So if we have a literal value, then our new packet just contains the literal value. Otherwise, we have an operator packet. And so this new packet will contain some subpackets. And then if we have the num packets, which was like one of the type length identifiers. We set the number of remaining packets for this packet. Otherwise, we set the number of remaining bits. Then we also set the version of the new packet, but that never gets used, and we set the type ID. Then we add this packet to its parent, which is the last thing on our stack. So now we need to consider, like, maybe we are done, maybe the parent has used up everything. So if jumping ahead to here, if the last thing on the parent, if the last thing on the parent counts its number of children via packets, then we decrement the number of packets that it has. And then we pop that from the stack if it doesn't have any remaining packets, because that packet needs no more children. But for the bits are counted across all of the ancestors. So if you have like one packet that counts how many remaining bits, and the first sub packet also counts how many remaining bits, like the third packet counts as bits towards both the first two packets, both its like parent and its grandparent. So we get the number of packets used by basically computing the length of our bits at the start before processing the packet. And then after we've processed it, we subtract the length after, and that's how many bits we've used. So we go through all of the packets in our packet stack, and if they track how many remaining bits they have, we remove the number of bits we used from that packet. Then we check for like the parent with the remaining packets, but then we need to basically do this like same thing, but for bit packets with bits. And the thing is, packets with bits can remove, like we can pop multiple things at once. And so while our packet, while the last packet in our stack, so while our parent doesn't have any remaining bits, we'll pop the parent. And finally, if we don't have a literal value, we put the new packet, which needs children, onto our packet stack. So that's that. So that gives us an actual like structured version of our packet. So now let me comment that stuff out. Oh no. Whoa. 2. So we end up with things like this. Subpackets. Let's do like 13. Where it's like 1, 3, and then a 2 and a 2, and then there's some other stuff. And then there's this. I still don't know how this gets in there. But whatever. That's a little iffy. Yeah, I don't know where those packets come from. Wait, where do those come from? Weird. Okay. So then for the other part of part 2, we now need to like evaluate these subpackets. So we look at the type ID. Literal values have their literal value. If it's a type ID of 0, we calculate the sum of the subpackets. 1 is product, 2 is min, 3 is max, 5 we check if the first one's greater than the second one. If so, it's 0, it's 1, otherwise 0. 6 is less than, 7 is equal. Pretty standard. So we just have to write a function to evaluate a packet. And so if it's a type, if it's a literal, these are my constants. If it's a literal, we just return the value of the literal. Otherwise, we evaluate all of the subpackets recursively. And then if it's a sum, we sum them up. If it's a product, we multiply them all. If it's min, we take the min. If it's max, we take the max. greater than, less than, equal, simple comparisons, and then 1 or 0. Else we return 0. So then, basically, yeah. Basically, we just the first thing in our packet stack is like the root, just so that we have something to put like the first packet in. So the actual root is the first child of the root packet, which is here, and so that's what we evaluate. But let's figure out where this like extra packet ID is coming from. All right, so I want this sub packets. So this is let's also do this. I want to see the packet ID first. So this root thing is packet ID 0, and then we have packet ID 1, and then packet ID 2, then packet ID 3, 4, then 5, 6, 7, then this is packet ID 8, and this is packet ID 8. Oh, I think those are just the zeros at the end. Let's see, is there a way to detect when I'm in that state? Maybe it's like something like this. If packet stack sub packets remaining bits equals 0, break packets there we go. So now this is basically like how I detect I'm done, because we have a root packet and it has no remaining bits or no remaining packets. Yeah, there we go. Boom. Cool. That one was a good one. Lots of examples. All right, that is Advent of Code, day 16. That was a fun one.